Welcome to DAR Tutors for online and home tuition. Today, we're going to explore a key chapter in IB Mathematics, Applications and Interpretation Higher Level. Chapter 9, Non-Right-Angled Triangle Trigonometry. By the end of this video, you will be able to calculate the area of any triangle using two sides and the included angle. Second, you will be able to apply the cosine rule to find missing sides and angles. Third, you will understand and apply the sine rule while carefully navigating the ambiguous case. And finally, you will be able to solve complex multi-step trigonometry problems that extend beyond simple triangles. These skills are fundamental for HL and will be demonstrated with rigorous IB-style examples. Let's begin. We'll start with the first objective, calculating the area of a triangle. You are likely familiar with the standard formula for the area of a triangle. It states that area equals 1/2 times the base times the height. This formula works perfectly when the height, which is the perpendicular distance from a vertex to the opposite base, is known. However, in many real-world scenarios, such as surveying a plot of land, finding the perpendicular height can be difficult or even impossible to measure directly. Fortunately, we can derive a new formula using trigonometry. The formula we are looking for is known as the trigonometric area formula. First, let's establish a standard convention for labeling a triangle. We label the vertices with capital letters A, B, and C. The side opposite vertex A is labeled with a lowercase a. The side opposite vertex B is B, and the side opposite vertex C is C. Now, let's derive the formula. We'll use this triangle labeled with sides B and C and the included angle A. The goal is to find its area without knowing the height directly. Let's consider an acute-angled triangle ABC. To find the area using our old formula, we need the height. Let's draw an altitude from vertex C to side AB and call the point of intersection D. This line segment CD, which we'll label H, is the perpendicular height of the triangle with respect to the base AB. Now we have a right-angled triangle ADC. Let's look at angle A. The sine of angle A is the length of the opposite side, h, divided by the length of the hypotenuse, b. So, sin A equals h over b. We can rearrange this equation to find an expression for the height, h. Multiplying both sides by b, we find that the height h is equal to b times the sine of A. Now we can substitute this back into our area formula, area L sin y fath base x height. The base is side C and the height is b sin A. This gives us the area formula, 1/2 C times B times sin A. Rearranging the terms, we get the more common form. Area equals 1/2 BC sin A. This formula holds true for any triangle, whether acute or obtuse, a fact we can prove using a similar process for the obtuse case. This leads to the general rule. The area of a triangle is half the product of two sides and the sine of the included angle. Using different pairs of sides and their included angles, we can also express the area as 1/2 ab sin C or 1/2 AC sin B. Let's apply this new formula to a worked example. This will solidify your understanding of how to use it. The question asks us to find the area of the given triangle. Here we have a triangle with two sides measuring 15 centimeters and 11 centimeters. The angle included between these two sides is 28 degrees. We need to find its area. First, identify your knowns. We have two sides and the included angle. Let's call the sides A and B. So A is 15 centimeters and is 11 naus. The included angle, which we'll call C, is 28 degrees. Next, recall the appropriate formula. Since we have sides A and B and included angle C, we will use the formula. Area equals 1/2 ab sin C. Now substitute the values we have into the formula. This gives us area equals 1/2 times 15 times 11 times the sine of 28 degrees. Calculate this value. It's a good practice to estimate to catch any errors. The sine of 28 degrees is about 0.47. Using a calculator, we find the area is approximately 38.74 square centimeters. Always include the correct units. Our second objective is to use the cosine rule to solve for missing parts of a triangle. The cosine rule is a generalization of the Pythagorean theorem. It relates the three sides of a triangle to the cosine of one of its angles. It states that a squared equals b squared plus c squared minus 2bc times the cosine of angle A. Remember our labeling convention? Side A is opposite angle A. The other two versions of the formula for b squared and c squared are just permutations of this. You can use this rule in two primary situations. First, if you are given two sides and the angle included between them, you can find the length of the third side. This is often called the SAS case, for side angle side. Second, if you are given all three sides of the triangle, you can find any of the three angles. This is often called the SSS case, for side. In the SSS case, it's often more convenient to use a rearranged version of the formula that solves directly for the cosine of the angle. For example, for angle A, the formula becomes cos A equals b squared plus c squared minus a squared, all divided by 2bc. Let's work through an example of the first case. Finding a side when you have two sides and an included angle. The task is to find the length of side BC, which we'll call A, in this triangle. We are given side AB, which is C, as 11 centimeters, side AC, which is B, as 13 centimeters, and the included angle at A as 42 degrees. We can see this is a SAS case, so the cosine rule is the correct tool. The formula we need to find side A is a squared equals b squared plus c squared minus 2bc t cos A. Here's the formula we will use. A squared equals b squared plus c squared minus 2bc c cos A. Now we substitute the values we know into the formula. We replace b with 13, c with 11, and a with 42 degrees. This gives us the equation. A squared equals 13 squared plus 11 squared minus 2 times 13 times 11 times the cosine of 42 degrees. Let's perform the calculation step by step to avoid errors. 13 squared is 169, and 11 squared is 121. Their sum is 290. Next, 2 times 13 times 11 is 286. Using a calculator, the cosine of 42 degrees is approximately 0.743. So a squared is 290 minus 286 times 0.743. This simplifies to a squared equals 290 minus approximately 212.5. So a squared is roughly 77.5. To find a, we take the square root. The square root of 77.5 is approximately 8.80. Therefore, the length of side BC is about 8.80 centimeters. Now let's look at the second case for the cosine rule. Finding an angle when you are given all three sides of a triangle. The problem asks us to find angle C in triangle ABC, given the lengths of all three sides. We have side A, opposite angle A, as 5 centimeters. Side B is 8 centimeters, and side C is 7 centimeters. We need to find the angle at vertex C. This is an SSS case, and the cosine rule is the only method. For finding an angle, we'll use the rearranged formula. The correct formula for angle C is EOSC equals a squared plus b squared minus c squared, all divided by 2ab. Let's plug in our side lengths into this formula. Substituting 5 for A, 8 for B, and 7 for C, we get cos C equals 5 squared plus 8 squared minus 7 squared, over 2 times 5 times A. Now we simplify the numerator and denominator. 5 squared is 25, 8 squared is 64, and 7 squared is 49. In the numerator, 25 plus 64 minus 49 equals 40. In the denominator, 2 times 5 times 8 is 80. This simplifies nicely to KOS C equals 1/2. To find the angle C, we need to find the inverse cosine of anifatus. In the context of triangles, where angles are between 0 and 180 degrees, the angle with a cosine of 1/2 is 60 degrees. So, angle C measures 60 degrees. The problem also asks us to find the area of the triangle. Now that we know two sides and their included angle, we can use our area formula from the first section. We'll use sides A and B, and the angle C we just found. Area equals 1/2 epsilon C. Plugging in the values, area equals 1/2 times 5 times 8 times the sine of 60 degrees. 5 times 8 is 40, and half of that is 20. The exact value of sin, 60 degrees, is the square root of 3 over 2. So the exact area is 10 times the square root of 3 square centimeters, which is approximately 17.3 square centimeters. We've seen how the area formula and cosine rule work. Let's move on to our third objective, the sine rule. The sine rule is another set of equations that connects the sides and angles of any triangle. It's especially powerful for situations that the cosine rule can't solve directly. The rule states that in any triangle ABC, the ratio of a side to the sine of its opposite angle is constant. You might also see it in its reciprocal form, which is useful when you're trying to find an angle. The proof is straightforward, using the area formula we already derived. We know that the area of a triangle can be expressed in three ways. Area equals 1/2 BC sin A equals 1 BC sin B equals 1/2 AB sin C. If we divide this entire equation by 1/2 sin B, the 1/2 cancels, and on the first term, the BC cancels, leaving sin A over A. On the second, AC cancels, leaving sin B over B. And on the third, AB cancels, leaving sin C over C. This gives us the sine rule. This demonstrates the rule directly from a concept we already understand. You should use the sine rule in two main scenarios. First, if you are given two angles and one side, you can find the length of another side. This is the AAS or ASA case. Second, if you are given two sides and a non-included angle, you can find another angle. This is the SSA case. However, as we will see shortly, this can lead to an ambiguous case, where there are two possible solutions for the triangle. Let's first use the sine rule in the straightforward AAS case to find a missing side length. We need to find the length of side B in this triangle, which is the side AC. We are given side C, AB, as 12 centimeters and angles B and C as 8 and 39 degrees respectively. To use the sine rule, we need a complete pair, a side and its opposite angle. We have side C, 12 centimeters, but we don't know angle C. The problem gives us angle C as 39 degrees, so our pair is CP12 and C39. We need to find side B. A quick check. The diagram shows side C opposite angle C, and angle B is at the vertex B. So the side given is AB equals C equals 12 centimeters, and angles are at vertices B and C. To find side B, we need angle B. We have angle B as 58 degrees. So we have a pair, C and C, and we want to find B and we have B. The rule to use is B sin B equals C sin C. So our setup is B over sin 58 degrees equals 12 over sin 39 degrees. Now we can solve for B by multiplying both sides by sin 58 degrees. This gives us B equals 12 times sin 58 degrees, all divided by sin 39 degrees. Calculating this with a calculator, we find that B is approximately 16.11 sin, so the length of side AC is about 16.17 centimeters. Now we arrive at a critical concept in trigonometry, the ambiguous case of the sine rule. Understanding this is essential for HL problems. The ambiguous case arises when you use the sine rule to find an angle in an SSA situation, meaning you are given two sides and a non-included angle. It's called ambiguous because for a given set of data, there might be two possible valid triangles, one unique triangle, or no possible triangle at all. Let's see why. Consider the equation sin θ equals k. For angles θ between 0 and 180 degrees, if k is positive, there are two possible solutions. An acute angle θ1 and an obtuse angle θ2 equals 180 degree f1. For example, if sin θ equals 1/2 θ could be 30 degrees or 150 degrees. The ambiguous case occurs when both the acute and obtuse solutions for an angle are mathematically valid in the context of the triangle's other given information. Let's analyze the possibilities. Let's explore the four possible outcomes when given sides A and C and the acute angle A. Case 1, no triangle. If side A is too short to reach the opposite side, no triangle can be formed. We can test this by calculating the height h, which is sec I sin A. If A is less than h, there's no triangle. Mathematically, this happens when using the sine rule to find the angle opposite side C. You get sin C1, which is impossible. Case 2, one triangle. If side EA has exactly the length of the altitude h, it forms a right-angled triangle, and this is the only solution. Alternatively, If A is longer than C, the obtuse solution for the angle opposite C would make the sum of the angles greater than 180 degrees, leaving only the acute solution. So, in both these scenarios, you get a unique triangle. This is a good point to invite you to contact our tutors. If these detailed explanations are helping you understand complex IB concepts like the ambiguous case, imagine the progress you could make with personalized, expert tuition. DAR Tutors offers support in IB, A-Level, and IGCSE. Visit our website or call us today to learn how we can help you achieve your academic goals. Case 3, the ambiguous case, a C-sin A and a C. This is the true ambiguous case. When A is longer than the height H, but shorter than side C, the arc for side A intersects the opposite side at two distinct points. This creates two valid triangles with two different possible sizes for angle C, one acute and one obtuse. It's crucial to identify the situation and provide both valid solutions. Failing to do so is a common error in exams. To summarize, whenever you use the sine rule to find an angle, be suspicious of a second solution, especially if the angle you're finding is opposite the longer of the two given sides. Let's work through an example that results in the ambiguous case. The problem is to find angle C in triangle ABC given the side lengths and angle B. We have side B equals 7 cm, side C equals 11 cm, and angle B equals 25 degrees. Notice we are given two sides, B and C, and a non-included angle B. This immediately signals a potential ambiguous case. We use the sine rule to find angle C. We'll use the ratio involving C and C and the ratio involving B and B since we have the full pair, B and B. The formula is sin C over C equals sin B over B. Substituting the values, we get sin C over 11 equals sin 25 degrees over 7. Solving for sin C, we get sin C equals 11 times sin 25 degrees, all divided by CZ. Calculating this, we find that sin C is approximately 0.665. Since the value of sin, C 0.665, is greater than 0 but less than 1, an acute angle exists. So we find the inverse sin A. The inverse sine of 0.65 gives us our first solution for angle C, which is approximately 41.7 degrees. But because this is an SSA case, we must check for a second solution. The sine of an angle is equal to the sine of its supplement. The second possible angle, C2, is 180 degrees minus the first angle, 41 degrees, which gives us approximately 138.3 degrees. Finally, we must check if this second angle is valid. The sum of the angles in a triangle must be 180 degrees. If C2 is 138.3 degrees, can it combine with the given angle B of 25 degrees? Yes, 138.3 plus 25 degrees is 163.3 degrees, which is less than 180. This means a triangle with C2 equals 138.3 degrees is possible. Therefore, there are two valid solutions. We must report both possible measures for angle C, approximately 41.7 degrees or approximately 138.3 degrees. For full marks, you must include both solutions. Our final objective is to develop a strategy for solving multi-step trigonometry problems that combine all the tools we've learned. These are very common in IB exams. When faced with a complex problem, it's not always obvious which rule to use. Here's a helpful flowchart. First, is the triangle a right-angled triangle? If so, use Pythagoras' theorem or the SOH-Ka-Toa ratios. If it's not a right-angled triangle, you must use either the sine rule or the cosine rule. How do you choose? Check the information you have. Do you have two sides and an included angle, SAS, or all three sides, SSS? If so, use the cosine rule. The cosine rule guarantees a single solution and is the safest choice in these cases. If you don't have SAS or SSS, you likely have two angles and a side, AAS or ASA, or two sides and a non-included angle, SSA. In these cases, use the sine rule. And remember our caution for the SSA case. The sine rule with two sides and a non-included angle requires you to check for two possible solutions. A final expert tip. In situations where either rule could technically find an angle, for example, if you have SAS and want to find one of the other angles, the cosine rule should be preferred over the sine rule. This is because the cosine rule produces a unique angle value between 0 degrees and 180 degrees, avoiding the ambiguity that comes from finding an angle's sine. Let's apply this problem-solving strategy to an IB-style question. We need to find the area of this quadrilateral PQRS and express it in hectares. A hectares is 10,000 square meters, but since our side lengths are in kilometers, let's remember that 1 square kilometer is 100 hectares. The diagram provides sides PQ, QR, and RS, and angles QPS and RQS. There is no single formula for the area of a general quadrilateral. Our strategy will be to divide it into two triangles, find the area of each, and sum them. The diagonal QS is drawn, dividing the quadrilateral into triangle PQS and triangle QRS. We will find the area of triangle PQS and the area of triangle QRS and add them together. First, let's find the area of triangle PQS. To do this using our formula 1/2 of P ab sin C, we need two sides and their included angle. We have PQ equals 8 clandent and angle QPS equals 70 degrees, but we don't know the third side PS or the included angle at Q. This means we first need to find another piece of information, and the most logical side to find is the shared side, the diagonal QS. In triangle PQS, we have two sides, 8 kilometers and 12 kilometers, and the included angle of 70 degrees. This is a SAS case, which means we can use the cosine rule to find the length of QS. Applying the cosine rule, QS squared equals 8 squared plus 12 squared minus 2 times 8 times 12 times QS 70 degrees. This calculates to approximately 144.5. Taking the square root, we find QS is about 12.02 kilometers. Now we can calculate the area of triangle QRS. We have sides QR out are 10, RS are 12, and the included angle RQS equals 30 degrees. Area QRS equals 1/2 times 10 times 2 times sin 30 degrees. Since sin 30 degrees is 0.5, the area is 1/2 times 10 times 2 times 0.5, which is 30 square kilometers. Now for triangle PQS. We have sides PQ 8, PS 12, and angle P 70 degrees. Area BPQS equals 1/2 times 8 times 2 times sin 70 degrees. This is approximately 45.1 square kilometers. The total area of the quadrilateral is the sum of these two areas. Total area equals 30 plus 45.1, which is 75.1 square kilometers. To convert this to hectares, we multiply by 100, giving 7510 hectares. A complete multi-step solution. Let's work through another problem. This one demonstrates how to solve a right-angled triangle that is part of a larger non-right-angled structure, a technique known as creating a right-angled triangle. We need to find the area of triangle PQR and then the length of the altitude from Q to RP. We have triangle PQR with side RQ equals 14, side RP equals 17, and the included angle R equals 37 degrees. First for the area. We have two sides and their included angle, SAS, so the area formula is perfect. Area equals 1/2 times RQ times RP times sin R. Substituting our values, area equals 1/2 times 14 times 17 times sin 37 degrees. This calculates to approximately 71.6 square meters, which we round to 71.603 for 3 decimal places as requested. Now for part B. Find the length of the altitude from Q to RP. Let's call the point where the altitude meets RP as D. The length we need to find is QD. Altitude QD forms a right-angled triangle, triangle RQD. In this right triangle, we know the angle R is 37 degrees, and the hypotenuse RQ is 14 meters. The altitude QD is the side opposite angle R. The sine of an angle in a right triangle is the opposite side over the hypotenuse. So, sin 37 degrees equals QD divided by 14. We can solve this for QD. QD equals 14 times sin 37 degrees. Calculating this gives us an altitude of approximately 8.425 meters. Notice the relationship. The area formula, 1/2 base x height and 1/2 ab sin c, are just different expressions for the same quantity. If we had used the altitude we just found, area is base RP 17, x height, QD 8.425 equals 1/2 17 and 8.425 diodes 7161, which matches our first answer. Both methods are valid. Let's work through one last IB-style problem that ties several concepts together. This involves a 3D rectangular prism. We need to find the measure of angle RPV in this rectangular prism. RPV is the angle formed by three vertices of the box. First, visualize the angle we need to find. It's the angle at vertex P within the triangle RPV. To find this angle, we'll use the cosine rule. But the cosine rule requires the lengths of all three sides of triangle RPV. This means we have a multi-step process. Step 1. Find the length of all three sides of triangle RPV. Step 2. Use the cosine rule to find the angle. Step 1. Find sides PR, PV, and RV. To find PV, consider the right-angled triangle PIV on the bottom face. Using Pythagoras' theorem, PV equals the square root of 6 squared plus 5 squared, which is the square root of 61. Next, for RV, consider the right-angled triangle RVW on the back face. RW is the same as PV, which is 5, and VW is 3. So RV equals the square root of 5 squared plus 3 squared, which is the square root of 34. Finally, for PR, consider the right-angled triangle PQR. PQ is 6 and QR is 3, so PR equals the square root of 6 squared plus 3 squared, which is the square root of 45. Great, we found the lengths of all three sides of triangle RPV. The sides are the square roots of 34 and 5. We now move to step 2. Step 2. Use the cosine rule to find the angle RPV. We are looking for the angle at P. Let's call this angle θ E. The formula for cos θ is the adjacent side squared minus the opposite side squared divided by 2 times the product of the adjacent sides. This gives cos θ equals 61.2 plus 45.2, 34.2 all over 2, 61.45. Squaring the square root simplifies the expression in the numerator to 61 plus 45 minus 34, which is 72. The denominator is 2 times the square root of 27.45. Simplifying the fraction, cos is 36 divided by the square root of 27.45. Finally, we take the inverse cosine to find the angle. The angle θ is approximately 46.6 degrees. So the measure of angle RPV is about 46.6 degrees. This problem was a great example of breaking down a complex problem into manageable steps. It's time to test your understanding with some IB-style practice questions. I'll display the question and you can pause the video to work on it yourself. Question 1. In triangle ABC, AC is 12 centimeters, AB is 10 centimeters, and the area is 45 square centimeters. Find the measure of the two possible angles at A. Pause the video now to solve the problem. Welcome back. Let's look at the solution. We have two sides and the area, so we use the area formula. Area equals 1/2 BC sin A. We can set up the equation. 45 equals 1/2 times 12 times 10 times sin A. This simplifies to 45 equals 60 times sin A. So sin A is 45 divided by 60, which is 3/4. Since the sign is positive, there are two possible angles. The first is the acute angle, inverse sine of 3/4, which is about 48.6 degrees. The second is the obtuse angle, 180 degrees minus the first, which is about 131.4 degrees. Both of these angles are valid, as they are less than 180 degrees. So we report both solutions. A is either 48.6 degrees or 131.4 degrees. Here is question 2. This is a classic ambiguous case problem, so remember to check for two solutions. Pause the video and give it a try. All right, let's solve this together. We have side-side angle, so we use the sine rule. The ratio is sin C over C equals sin B over B. Substituting our values, sin C over 11 equals sin 40 degrees over A. Solving for sin C, we get 11 times sin 40 degrees divided by 8, which is approximately 0.883. The first solution is inverse sine of 0.883, which is about 62.0 degrees. This angle is acute. The second solution is the obtuse angle, 180 degrees minus 62.0 degrees, which is 118.0 degrees. Now, we check if this obtuse angle is valid by seeing if it can form a triangle with the given angle B of 40 degrees. 118.0 plus 40 equals 158.0 degrees. This is less than 180 degrees, so it's a valid triangle. We have two possible solutions. The two possible values for angle C are 62.0 degrees and 118.0 degrees. Question 3 is a 3D problem similar to the worked example. This problem requires you to find the lengths of three diagonals using Pythagoras' theorem in 2D planes and then use the cosine rule. Pause the video and solve it. Let's review the solution. First, let's establish the lengths of the sides of triangle EDG. We'll use the vertices E, D to G. ED is a diagonal on a 3x6 face, so ED equals the square root of 3 squared plus 6 squared, which is the square root of 45. DG is a diagonal on the bottom face. It connects the corners D and G. In the rectangle DCG, it forms the hypotenuse. The sides are 4 and 6. So DG equals the square root of 4 squared plus 6 squared, which is the square root of 52. Finally, for EG, we can form a right triangle on the top face with sides 4 and 3. So EG equals the square root of 4 squared plus 3 squared, which is the square root of 25, or 5 meters. Now we have triangle EDG with sides 35, 213, and 5 meters. We need to find the angle at D, which is EDG. We use the cosine rule. As D equals ED2 plus DG2, EG2, 2 by x of EDX DG. Substituting the squared lengths, we get 45 plus 52 and 25 in the numerator, which is 72. The denominator is 2 times 35 times 2 and 13, which is 1265. So COSD is 6 divided by the square root of 65. Taking the inverse cosine of this value, we find that the angle EDG is approximately 41.9 degrees. Here is question 4. This is a classic IB multi-step problem that combines the cosine and sine rules. Part A requires the area formula. Part B requires the cosine rule. Make sure to consider both possible angles from Part A for Part B. Pause the video and work it out. Let's begin the solution. We have two sides, 4 and 6, and the included angle is theta. The area is 11.6 square meters. Part A. Find θ. We use the area formula. Area equals 4 pi 6 by sin θ. This is 11.6 equals 12 sin θ. So sin θ is 11.6 divided by 12, or about 0.9667. Again, there are two possible angles. The acute angle θ1 is inverse sine of 0.9667, which is about 75.2 degrees. The obtuse angle T2 is 180 degrees minus 75.2 degrees, which is 104.8 degrees. Both are valid as angles within a triangle. Part B. Find the length of the third side. Let's call it x. We must consider both possible angles from Part A. This is a say-s case, so we use the cosine rule. Case 1. Angle θ is 75.2 degrees. x2 equals 42 plus 62, 2, 4, 6, 75.2 degrees. This gives x2 42.1, so the third side x1 is about 6.49 meters. Case 2. Angle θ is 104.8 degrees. x2 equals 42 plus 62, 2, 4, 6, 104.8 degrees. This gives x2 68.1. So the third side x2 is about 8.25 meters. Notice how the two possible angles from the area formula lead to two possible lengths for the third side. A complete answer provides both. Our final practice question is a classic bearing problem. Bearings are always measured clockwise from north and are a common feature of IB trig problems. The problem describes two yachts, the Porpoise and the Queen Maria, in relation to a lighthouse. The first and most crucial step is to draw an accurate diagram. Let's place the lighthouse at the origin, 0 so such. We draw a north line at L. The Porpoise P is 2.4 kilometers away on a bearing of 223 degrees, which is in the third quadrant. The Queen Maria Q is 2.1 kilometers away. We don't know her bearing, but we know the angle at M is 53 degrees. To find the distance between the yachts, we need the length of the side PQ. This is the third side of triangle LPQ. We have two sides, LPT 2.4, LQCUS 2.1, and an angle at Q, LQM 53 degrees, but it's not the included angle, PLQ. This is an SSA case, which might be tricky. An easier approach is to find the angle at the lighthouse, PLQ, and then use the cosine rule. We need to find the bearing of the Queen Maria first to find this angle. Let's use the sine rule in triangle LQM to find the angle at the lighthouse, MLQ. Sin MLQ, LQ il sin LT LP. This gives sin MLQ 0.698. The acute angle is about 44.3 degrees. The obtuse angle is 180 degrees. 44.3 degrees is 135.7 degrees. The problem states the porpoise is to the right of the lighthouse. Our bearing for the porpoise is 223 degrees. To be to the right means the Queen Maria's bearing must be between 223 degrees and 223 degrees PS 180 d is 403 degrees. So an angle of 44.3 degrees is correct. Now we find the bearing of the Queen Maria. The bearing is 223 degrees minus 44.3 degrees, which is 178.7 degrees. The angle PLQ equals 180p, 223, 178.7 equals 135.7 degrees. We now have triangle PLQ with sides LP 2.4, LQ 2.1, and the included angle PLQ equals 135.7 degrees. This is a SAS case, so we use the cosine rule. PQ2 equal LP2 plus as LQ2, 2 LP, LQ, PL. This gives PQ2 19.3, so the distance PQ is approximately 4.4 kilometers. This detailed process shows the importance of both diagrams and a systematic approach to solving complex trig problems. Let's quickly recap what we've learned. First, the area formula for any triangle is 1/2 ab sin C. Second, we use the cosine rule for SAS or SSS cases. Third, we use the sine rule for AAS or SSA cases. But for SSA, we must be careful to check for the ambiguous case, which can have 2, 1, or 0 solutions. Fourth, for complex problems, drawing a clear diagram and deciding on the correct rule is the key to success. Remember, when finding an angle, the cosine rule is safer than the sine rule. These tools are essential for success in IB Mathematics AIHL. By understanding the formulas, knowing when and how to apply them, and practicing with a variety of problems, you will master non-right-angled triangle trigonometry. Thank you for watching. For more expert tuition in IB A-Level and IGCSE curricula, please visit dartutors.com or contact us today. Our dedicated tutors are ready to help you excel.